Let's look at the concept of critical values, how you find them, and what that all means for finding confidence intervals using the z and t distributions. We've used the z distribution before. This is just a normal distribution, which we can draw in Stapplet. And the z distribution has a mean of 0, standard deviation of 1. Just to orient this right in the middle and make each tick mark worth 1, so that's 1 standard deviation to the right of the mean, left of the mean, 2, 3, and so on. And that first standard deviation is always going to land right below the inflection point where it flattens out here. A critical value is just another word for a cutoff point. In this case, we want a cutoff point that will give us a 90% of outcomes similar to the center or mean outcome. So it's basically saying how many standard deviations over do we need to go to capture 90% of this curve. To do that, since we're entering an area, we're going to change the operation to the inverse normal, calculate a value corresponding to an area, the central area of 0.9 for 90%. You might have an input that actually says percent here. It would have to do with how you have your preferences set up. So check those if yours looks a little different. Make sure you just read it carefully. You could test out a similar problem to see if it's set up the same. Here we see that we're going 1.64 approximately standard deviations to the right and the left of the mean to get 90% of similar outcomes. If we were to apply some context to this problem, like if we had a really solid value for standard deviation, we know that these vary by maybe about 10 on average, and we have a mean of 50, then we could definitely turn those into numbers and get cutoffs like lower bounds and upper bounds. But we'd have to use all the concepts of the central limit theorem, sampling distributions. So that's all coming up, and we do that a totally different way. But we will just use this normal distribution if we ever need to know how many standard deviations over we're going to go. For number 4, it just adds a layer to it. To find a right tail area, I recommend just grabbing your calculator. First, you'll find alpha. Alpha is 1 minus the confidence level as a decimal usually. So 1 minus 0.899, and then you divide alpha by 2. To visualize it, we're just saying how much area is outside the curve. So that's 1 minus c, and then each tail, there's 2 of them, divide by 2. So this was 899 actually, 0.0505 was that answer for that one. And I already showed you that critical value. The other 2 problems I have in this section have to do with t. One of them has a bunch of percentages and probabilities with t. The other has to do with confidence levels. We've already talked about confidence levels and confidence intervals, but we haven't really talked about why there's a need for t. And t has to do with the fact that when we are estimating the mean and standard deviation, which is what you're going to be doing starting in problem 11, you have a sample, and that sample gives you a mean, which kind of tells you where to put the middle of the distribution. And then it also has a standard deviation, which tells you approximately how spread out these values are. The problem is, when we have small samples, really when we're under about 300, we'll start to notice that our standard deviation is not very accurate. And so if we want to figure out our margin of error, or how wide apart similar samples will be spaced, when we're not using an accurate idea of the spacing and variation, we can get wrong answers a lot. So the t-distribution is going to account for small samples. I'll also use Stapplet for that. This is under probability, and it has this degrees of freedom input. Degrees of freedom is n-1 for most situations. If we're doing x, y, 2 variable scatter plots and correlation, we'll do n-2. Engineers might do n-3, 4, 5. It's always n minus the number of variables of the system. This is just one variable stats that we're doing, so n-1. I guess on my first problem that I have for this, it just gives me the degrees of freedom, so I don't need to worry about it. For confidence intervals and critical values, they're going to give you a sample size, so you got to do your n-1. And in this case, that's 6 degrees of freedom. That's what my curve would look like, and then I need to find my center area of 98% and see what values correspond to that. And that means about 3.14 standard deviations to the right and left of the mean will capture 98% of similar samples when I have a sample size of 7. So all that information goes together. And the nice thing here is you can actually adjust the sample size and see how it affects it. So if we made the samples smaller and smaller, you're going to see that blue go farther and farther to the right just because we're smushing it down. And we're seeing less of a high peak in the middle and more variation. And it's just because with small samples, we don't expect to have a very good estimation of that variation. So we're kind of just inflating our answers. Any other problems you have, you're just working with probability. It's a lot like the problems in the last couple chapters with the normal distribution. So enter your degrees of freedom or your n-1, and then either calculate the area for probability problems, like this one was to the right of 1.75, or find the inverse operation by calculating the value and inputting your area. Percentile, for example, is a left tail. I think I saw one that was the 10th percentile, and that would look like this, with a t-value of negative 1.35.